Now we are going to talk about the hydroboration reaction. The hydroboration of an alkene followed by oxidation is also going to give us an alcohol, but this alcohol is definitely different from the alcohol that we got using acid catalyzed hydration. Now let's see how this is going to be different and the mechanism for hydroboration followed by oxidation. So here is the general reaction wherein you have an alkene. In the first step, it is reacted with borane in the presence of THF. THF is going to act as a solvent. And in the next step is the actual oxidation taking place where the BH2 is going to get converted into hydroxy group. So for which we'll be taking a base and also hydrogen peroxide in water. This is going to form an alcohol. When you consider the structure of borane and methyl cation, they both are going to act as an electrophile. Borane is acting as an electrophile because it has got an incomplete octet, which means it has the ability to accept electrons to complete that octet to make it stable. The two alcohols that you will be getting from acid catalyzed hydration and hydroboration followed by oxidation are different. Here you have the hydroxy group attached to the carbon which has the most number of alkyl groups. But here the hydroxy group is attached to the carbon which has the most number of hydrogens. So obviously these two are constitutional isomers, and depending upon what the final product that you need, you can conduct any one of these reactions. Let's now look into the mechanism for hydroboration reaction. The mechanism is going to be concerted, where bond breaking and as well as bond forming happens all at the same time. Okay? A concerted reaction is the reaction where bond formation and as well as bond breaking is going to happen at the same time. Now here again, nothing has changed with respect to Markovnikov's rule. But the electrophile is going to be changed here. Here, it is not the hydrogen which is going to act as an electrophile, but it is the BH2. It is the boron in the BH2 that's going to act as an electrophile since boron has got an incomplete octet. So this is our electrophile, and therefore this hydrogen ion is going to be our nucleophile. When we apply a Markovnikov rule, the electrophile needs to go get added to the carbon which has the most number of hydrogens. So this is the carbon where the BH2 needs to get attached to. And the nucleophile is going to go on to this carbon. So the nucleophile is going to be the hydride ion. This is going to go on to this carbon. The product for this reaction is an alkyl borane. Now how this alkyl borane is created from alkene. The electrons from the double bond is going to make a nucleophilic attack on this electropositive boron. As these electrons try to come in, the bond between the hydrogen and boron is going to break and it's going to move towards the carbon to form a new bond. So here are the two new bonds that are obtained, and the two new bonds are created in exactly the same direction. So which means it is sudden addition. BH3 has got three potential hydride ions. So the alkyl borane, which is formed in the first electrophilic addition, can further react with alkenes to undergo second electrophilic addition and third electrophilic addition to give a dialkyl borane and trialkyl borane respectively. But when you use 9-BBN, which is 9-bora bicyclononane, it's only going to lead to the monoalkylation because it has got bulky R groups on it. The hydroboration reaction is followed by oxidation, where the BH2 or the Br2 is going to get converted into an OH, thereby forming the final product alcohol. So here the OH minus is going to act as a base, and the H2O2 is going to act as an oxidizing agent. Mechanism for the oxidation reaction. To begin with, hydrogen peroxide is going to make a nucleophilic attack on the electropositive boron, thereby forming more like a tetrahedral intermediate. But this tetrahedral intermediate has a negative charge on the boron. So in order to get rid of the negative charge, 1,2 alkyl shift needs to happen. So this propyl group is going to shift to the neighboring position, neighboring oxygen, thereby thrusting out the hydroxide ion. Once this hydroxide ion is thrusted out, it's going to come again to make a nucleophilic attack on this boron again to create another intermediate where again the boron is going to have this negative charge. And in order to get rid of this negative charge, the alkoxide ion is going to leave, the propoxide ion is going to leave, which will go and grab a hydrogen from the water molecule to form the alcohol that we need. Will there be any carbocation rearrangements happening in the hydroboration followed by oxidation? The answer is no, right? Because there is no carbocation rearrangements happening here. The mechanism doesn't involve any carbocations, and therefore there is not going to be any carbocation rearrangements happening. And therefore you can easily predict the product where the electrophile is going to get added to the carbon which has the most number of hydrogens. So once this is converted into BH2 and you have an hydrogen on this carbon, right? This BH2 is going to get converted into an OH in the next step, giving us 3-methyl 1-butanol. So there is not going to be any change in the structure, the skeletal structure. Okay, so all the carbons are going to be exactly in the same place as your starting material.